So today's lesson is lesson 14, modeled and guided instruction from the instruction book, page 132 and 133. Says, learn about determining the number of solutions of an equation. Read the problem below, then explore how to identify when an equation has only one solution, infinitely many solutions, or no solution. Yari and her friends, Alyssa and David, were each given an equation to solve. Yari was given the equation 2 times, in parentheses, x plus 10 minus 17 equals 5 plus 2x minus 2. Alyssa was given the equation 5x plus 3 minus 3x equals 2 times, in parentheses, x plus 3 minus 5. David was given the equation 2 times, in parentheses, x minus 3 plus 9 equals 5 plus x minus 1, whose equation has only one solution, infinitely many solutions, and no solutions. So we can model it. We can use properties of operations to simplify each side of Yadi's equation. So we're given 2 times x plus 10 minus 17 equals 5 plus 2x minus 2. We can use the distributive property here and multiply the 2 times the x and the 2 times the 10. That gives us 2x plus 20. On the right side, we combine our numbers, leaving the variable alone. So 5 minus 2 gives us 3. Then we can simplify further by combining the 20 and the minus 17, giving us 3. So then we're left with 2x, bringing it down, the 3 from this, bring down the right side. And so we have simplified Yadi's equation to be 2x plus 3 equals 3 plus 2x. In this little picture, it says the variable terms and the constant are the same on both sides of the equation. No matter what value you choose for x, the equation will always be true. Because if you look at this, 2x on one side, 2x on the other, 3 on one side, 3 on the other. This is a balanced equation. That means that this would be like, if we wanted to, we could rewrite it as 2x plus 3 equals 2x plus 3. And that means it would be a true statement. And that means that no matter what you put for x, it's always going to be true. So Yadi's equation has infinitely many solutions, okay? So hers is the one that has infinitely many. I'm going to put her name here, Yadi. Hers has infinitely many solutions. Now, if we look at the next one, Alyssa's equation, we're going to use properties of operations to simplify each side of Alyssa's equation. So the first thing they did was combine their x's. 5x minus 3x gives you 2x. Bring down the positive 3. On the right side, you distribute that 2 using the distributive property. So 2 times x gives you 2x. 2 times 3 gives you 6. Then you can simplify the right side. 6 minus 5 gives you 1. Bring down the 2x. And the left side, there's nothing else you can simplify. You just bring it down. 2x plus 3 on the left. So now if we're looking at the picture, it's no longer balanced. The right side is a little bit higher. The left side is heavier because they have more individual digits. So there's 3 on this side and 1 on this side of the little green blocks. Those represents the value of the 3 and the 1. So the variable terms are the same on both sides of the equation, but the constants are different. The plus 3 is different than plus 1. There is no value for x that will make the equation true. If you weren't sure just by looking at it, you could plug in a 1 on both sides and see, are you going to get the same thing on both sides, or a 2 or a 0? And no matter what number you plug in, it will not work because this plus 3 is different than this plus 1. So this one is no solution. Alyssa is no solution. So up here where it said no solution, I'm going to write Alyssa's name. The last one is David's equation. Hopefully his comes up with only one solution because that's the only option left. And if we get his to be the one solution, then that means the other two are probably right. You can use properties of operations to simplify each side of David's equation. So on the left, they're going to use distributive property. 2 times x gives you 2x. 2 times negative 3 gives you negative 6. And then bring down the positive 9. 5 minus 1 gives you 4. Bring down the x. Then they combined the negative 6 plus 9 on the left side. That gives them the 3. Bring down the 2x. And then bring down the 4 and the plus x. So here in the picture, they have 2 x's on one side, 1 x on the other. 3 on one side, 4 on the other. It stays balanced because this number replaces that x. The variable terms are different. There is only one value for x that will make the equation true. So it's still balanced because there's still the same amount of like things weighing down the scale. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the scale's still balanced. That's how you know that there's gonna be a solution. But because it's not the exact same on both sides, that's how you know it's gonna be only one solution. So we could actually, if we wanted to, prove that it's only one solution by going further, and we could subtract x on both sides. These would cancel out here. Then we would have 2x minus 1x is just 1x. Subtract the 3 on both sides so that these 3's cancel out. So then 2x minus x is x. The 3's cancel out. These x's cancel out. And then 4 minus 3 is 1. So then x would... that's supposed to be equals. X would equal 1. That's only one solution. So David's is the one that has only one solution. Okay? Let's take a look at page 133. Connect it. Now you will use the models to solve this problem. Look at model it for Yadi's equation. What do you notice about both sides of the equation? What equation do you get if you subtract 2x from both sides of the equation? So what do we notice about hers? Well, it was balanced, first of all, right? The equation was balanced on both sides of the equal sign. And now they're saying if we take 2x away from both sides, minus 2x, we would be left with 3 equals 3. Okay, that's what they're asking us to do. So what do you notice about both sides of the equation? Let's say both sides are the same or they are balanced. Both sides are equal. And then what equation do you get if you subtract 2x from both sides? If you subtract 2x from both sides, you subtract 2x from both sides, you get 3 equals 3. Number 3, look at model it for Alyssa's equation. How is it different from Yadi's equation and how is it similar? So if we're going to look at these two, comparing them. Oh, wait, these two, comparing them. Alyssa's and Yadi's. Alyssa's is not balanced. Yadi's is balanced. It's similar because it still has the same like number of x's. It's just the constants are different. So everything is the same about these two scales except for the little green blocks, which are representing the constants in the equation. So we can say that Alyssa's equation or Alyssa's equation is different because it's not balanced. Alyssa's equation is not balanced. Both variables in Alyssa's equation and Yadi's equation have the same coefficient. The constants are not the same. That's the part that's different. Okay. Number 4, look at the pan balance for Alyssa's equation. Is there any way to balance the pans? Explain. What equation do you get if you subtract 2x from both sides of the equation? So we're looking at her balance, her scale. They're saying, is there any way to make this equal? I guess... I mean, if you look at, Alyssa's her pans, there's nothing we can do to make them balance. Like, if we look at this equation, if I subtract 3 from both sides, this side's going to have 2x by itself, and then this side will have 2x minus 2. Like, if I subtract 1 from both sides, then I'll have 2x on one side and 2x plus 2 on the left. So, I mean, and then if I combine my x's, then I wouldn't have, if like they said, subtract 2x on both sides, we would be left with 3 equals 1. So no matter what we do, the pans will never be balanced. So let's add that. Let's write that down over here. No matter what we do to the pans, or to the equation, let's say that, due to the equation, the pans will never be balanced. If we subtract 2x on both sides, we will have 3 equals 1. Number 5, look at model it for David's equation. Are the variable terms on each side of the equation the same or different? And then solve David's equation, which we already did, right? So let's go back and look at that. It says, are the variable terms on each side of the equation the same or different? Variable terms on each side, well, the variable terms were different. We had 2x on one side and 1x on the other. So the variable terms were different. Or was that? I'm going to go with different. And if we solve David's equation, we ended up getting x equals 1. So for David's equation, we're going to say x equals 1. Explain how you know when an equation has only one solution, no solution, or infinitely many solutions. So an equation has infinitely many solutions when you get a true sentence like 3 equals 3. That's what we've been talking about. So when an equation has infinitely many solutions, we get a true statement like 3 equals 3. Oops, 3. An equation has no solution when you get a false statement. So when we get a false statement, like 3 equals 1, the equation has no solution. Solution. When the variable terms on both sides are different, the equation will have only one solution. So I'm just going to show you really quick. So this one, right, it was the same on both sides. 2x plus 3 equals 2x plus 3. The variables were the same. The constant was the same. That's going to be infinitely many solutions. For the second one, the variables were the same, but the constants were different. That's going to be no solution. And then this one, the variables were different and the constants were different, but we can solve and figure out what x is. That's when there's only going to be one solution, when the variables are different and we can solve and get x by itself. On a no solution, you'll get a false statement, 3 equals 1, right? We solved it and we got 3 equals 1. False statement makes it no solution. Here we got 3 equals 3. That was a true statement, so it makes it infinitely many. And here when we solved, we ended up getting x by itself and we got only one solution. So in order for it to get only one solution, the variable terms on both sides are usually different. So I'm going to say when the variable terms on both sides are different, the equation will have only one solution. Try it. Use what you just learned about equations with only one solution, no solution, or infinitely many solutions. Show your work on a separate sheet of paper if you need to. It says replace C and D in the equation. Cx plus D equals 8x plus 12 with the given values. Tell whether the equation has only one solution, no solution, or infinitely many solutions. I'm going to get me a scratch paper here so I can write this down. Give me 1 second. Okay, so I wrote down the equation Cx plus D equals 8x plus 12 For number 7, they told us that C equals 6 and D equals 34, so I went ahead and filled that in. Now I have 6x plus 34 equals 8x plus 2. So far, our variable terms are not the same, and our constant is not the same. So the only way to figure out if it has one solution, no solution, or infinitely many solutions is to now like simplify. So I would say if we subtract 2 on both sides, we would get 6x plus 32 equals 8x. We could get our x, move it from the left side to the right by subtracting 6x on both sides. These would cancel out. We would have 32 equals 2x divided by 2 divided by 2. X, divided by 2 on both sides. X would equal 32 divided by 2, which is 16. So for number 7, there's only one solution because the variable terms were different on each side of the equation, and the... Oh man, this was supposed to be a 12, not a 2. Now I have to redo it. I made a mistake, and it happens to everybody. So let's take another look at this. 6x plus 34 equals 8x plus 12. So let me try this one more time. I did make a mistake. You guys saw that, so I'm going to go ahead and make an x over my mistake and redo it. Minus 12 minus 12. Left with 8x on the right. Those 12s cancel out. 34 minus 12 is 22. Okay, now I'm going to subtract 6x on both sides. I'm left with 22 on the left. 2x on the right, divided by 2, divided by 2. X equals 11. Okay, so I still only got one solution. I was just originally the wrong solution. My bad. So for number 7, x equals 11. I would say only one solution. Okay. Now let's do number 8. So I still have the original equation here at the top of the page. Now C is going to be 8 and D is 6. So C is 8. That means I have 8x and then plus 6 equals, on the right, 8x plus 12. Okay, right off the bat, the variable terms are the same, but the constant is not. So my first assumption, based on what we just learned in today's lesson, is that this is going to have no solution because the constants aren't the same, but the variables are. So I'm going to try it just to see. I'm going to kind of play with it. If I subtract 6, I'm left with 8x equals 8x plus 6. Already not making sense. If I subtract 8x on both sides, these cancel out. I'm left with 6 equals 0. This is not a true statement. This is false, which means that there is no solution. So I would just write 0 equals 6, no solution. Okay? And that concludes today's lesson. Your assignment for today is to do, let me see what page is out of your practice book. Yesterday, you guys did 149 and 150. Today, you're going to do page 151 and 152. All right, have a good day.